Hey, Professor.
Hey guys, welcome back to my channel. It is now a channel.
Yup, I see that. I have actually a suggestion if you wanna hear it.
What's up?
I have a suggestion if you wanna hear it.
I love suggestions.
Okay, so like how you named the videos by like the dates, it's not bad, but if someone not from our course, it would be better if you in the title like just mentioned what we were doing in the lecture.
Yeah,
So they
I
just
hear you.
when they search up like this method, like your video comes up to them because it's already in the title.
Yes, you are absolutely correct. As a rookie mistake I made, as just a noob in YouTubing, I will change the titles. I have the subjects covered in like the description, but it's better to do it the other way around. It's better to put the subject in the title. And
Yeah, it will
probably give a shout out to City College somewhere in there too.
it will help make it more popular among students who are looking for something.
Yeah, for sure. And like if any one of you guys, wants a plug for your channel, just let me know. I'm happy to facilitate. Um,
Thank you.
uh, that was mostly in jest, but I seriously, I'm happy to do it. Um, I think we're all here. A few of you are still recovering from the weekend. Let's see. For those of you that haven't sent your shipping information to Tariq, please do so. Thank you, Christopher. Yeah. You know what? Someone should make a logo for the course, for the channel, for the course. That would be awesome. It's
Um,
it's unfortunately pro bono work. I can't compensate you.
I'll start right after class.
Okay.
I also have a suggestion
Yeah.
because I was watching the videos this weekend, and I think it's better if maybe you like read some of the questions from the chat, because when you're watching the video, you don't know what they're asking, and it's like you answering the question, but like as the
Oh,
viewer,
that's a
you don't
good
know what it is.
question. Yeah, so that's a good point. Yeah, that's right. Yeah, because I'm up here. Yeah. I definitely should read it back. The ideal solution would be for Zoom to integrate the chat window into the same way that they put whatever the thumbnail of me teaching at the corner. They should also have like the running chat. But yeah, you're right. I should totally read the question as long as it's appropriate. Okay. I think there was some concern about copyright, but the course uses slides, and so the slides are actually made. They're homemade. They're not from any publisher, so I think we should be fine. Yeah.
Yeah,
So
just a reminder, the homework will be due in, I think, on Wednesday. So please take your time to review your submission before you actually submit it. I think don't make silly mistake.
thank you, Sam. That's right. They are due at 11:59 p.m. 0.999999999 seconds.
Also, Professor, you allow multiple submission, right?
Oh yeah, no, I'm okay. Yeah, absolutely. If somebody like notices a mistake in their initial submission and wants to resubmit, that's fine.
Okay.
The only thing I care about is you guys do your own work as much as possible. Again, discussing the problems is fine, but as long as when you sit down to write it, it's coming from your brain onto the paper, that's fine. There's no way that if you don't do the homeworks, there's no way that you'll get a good grade on the exams. Let's put it that way. There's just no way. Things, I hope that no one has to learn that the hard way. Okay. Any other questions? If not, no, deadlines are deadlines. I mean, I don't know. I think I nominally take 20% off every day. I guess if you email it to me, 12:01 a.m. Eastern on Thursday, I won't give you a 0, but yeah, before the deadline, yeah, that's what Sam was just saying. We're allowed multiple submissions. Yeah, and it's usually 20% off per day, unless you have a medical emergency. And I read those notes. I know all of you have doctors in your family. I'll follow up on those notes. Okay. Oh, someone's already had enough. Okay, today we are picking up where we left off last time. This is slide deck number 4. For me, this is slide 17. Oh, hold on, I will admit you. You get good luck getting the doctor to sign off on that, Kuzema. All right. Let's see. Hope everyone is enjoying. Oh wow, it's just Zoom with a little update. They put the speaker bar at the top for me. I'm not sure if I want that though. Very interesting. Okay, source transformation. Can you guys see the entire slide?
Yeah, we see it, Professor.
Okay, great. So source transformation is another technique in your toolbox for analyzing circuits. I'll just give you the Coles notes right now. I guess it's called Cliff's Notes in America. You guys may be too young to even know what those are. Anyhow, the basic idea of source transformation is that you can replace a battery that's in series with a resistor with a current source in parallel with that resistor, right? And that sometimes helps you. Like sometimes you have a circuit that has like 10 batteries and 1 current source, and it will be easier to analyze if you only had batteries. So you can swap out the current source for a battery, and it's not a difficult concept. I'll try to do my best to convince you that this is a valid substitution, right? So if the voltage and the current at the terminals, the input terminals, are the same, then you haven't changed anything in the circuit, right? The voltage and the current characteristics stay the same. The circuit is equivalent, right? Okay. And so sometimes, like, again, as I was saying, if you have a circuit that has mixed sources, so some voltage, some current sources, sometimes it's advantageous for you to swap out a current source for a voltage source, or sometimes a voltage source for a current source. And so the reason for that is if you want a fully series circuit, you'll only want batteries. If you want a fully parallel circuit, like one big parallel branch, you'll want current sources. And you'll see what I mean in just a second. So this is known as source transformation. So it's a process where you replace a voltage source in series with a resistor by a current source in parallel with that same resistor. So the only thing that you have to do when you do this transformation The only thing that you have to do when you do the transformation is make sure that if you have a 10-volt battery in series with a 10 ohm load, and you want to swap that with a current source in parallel with a 10 ohm load, you'll have to know what the value of that current source is. So that's basically what we're going to show you next. So here are two pictures. And my claim to you is that if you are sitting at terminals A and B in this picture, and if your friend is sitting at terminals A and B in this picture, under certain conditions, you guys are looking at the exact same circuit. Even though you're looking at a battery and your buddy's looking at a current source. So my question to you is, under what conditions are these two pictures equivalent? So the resistors are already equivalent. So what has to be true about the value of Vs and about the value of Is for these two circuits to be equivalent? Any ideas?
A constant R.
What's that?
A constant R.
Yeah, so R is going to be constant for sure. It's actually
Linear. Like I'm trying to say they're linear. Like the R is the slope is the same for both.
Yeah, I think you're on the right track. Basically, you would like, well, let's actually do this systematically. So we know that these two pictures are equivalent if the voltage and currents at A and B are the same, right? So let's turn off the sources. Okay, let's measure let's measure the equivalent resistance. So if you sorry, let's short circuit A and B. Sorry, not turn on. Let's short circuit A and B. So let's draw a short circuit. So just a wire. That's another way of saying that is, let's connect a wire between point A and point B here. So I'll annotate this, even though it's going to cause me software problems. All right, so now I've short circuited A and B. And so my question to you is, first on the left, how much current is flowing down here? Yes, Vs over R. Excellent. Oops. Why is it not letting me undo? Okay. Let me move this over here. Right. So if you short circuit, I'm going to draw this just because I feel like. So you connect these, and then like Christian, you said, the current that flows around this loop is equal to Vs divided by R. Now, what is the current in this picture that flows from A to B? Is. That's right. And the reason that Is flows there is because this current source, the current's going to make a right turn, is going to hit this junction, and it's going to bypass the resistor because it has a zero impedance path on the outside, right? So this current source will just send current around the outside of the circuit, and it will completely avoid the resistor. And so the current flowing from point A to point B is equal to Is. In other words, these two pictures are equivalent if Vs over R is equal to Is, which is basically a statement of Ohm's law, right? So if you multiply Is times R, you get Vs. All right. Now the other case, right? So VS over R is required for the two circuits to be equivalent. Let me see. I think there's one more case that we have to look at. The other thing that I should point out is I'm going to undo a lot of these clear. So notice that if we open circuit A and B, right? If I open circuit A and B, so I don't connect them, what is the voltage here? What is the voltage between point A and point B in this picture?
Zero.
Zero is the common guess, and that is what
Oh.
almost everyone says. Zero is not the voltage though. But again, that's a mistake that most students make at this point of the course. Yeah, it's VS. The reason it's VS is because, oh, there goes my cursor. My new computer has Catalina as the OS, and I cannot get some software to work with it, so I'm stuck with this beast.
Yeah, I think one of the easy way to remember this thing is that like if you are working, like you will do this in the lab kit work, but like if you want to measure the voltage, you you will put the voltmeter in parallel with the resistor or whatever circuit component you want to measure the voltage. But if you want to measure the current, you put it in series with the loop. So like that means in parallel, like the voltage in parallel will be equal to like whatever like the circuit component in the loop.
Yeah, exactly. So if you in this, like let's say you're in the lab and you connect a battery to a resistor, but then you don't complete the circuit. And if you put your voltmeter here, your voltmeter will still sense this battery. There will not be any current flowing across here because there's no complete path for the current to flow. However, in this picture, the voltage between point A and point B is equal to Vs. And in this picture, the voltage between point A and point B is equal to Is times R, because this current now flows through the resistor, right? And producing a voltage of Is times R across the resistor, which is parallel to the terminals A and B. So the reason I say all this is in these two pictures, if A and B are short-circuited, they're equivalent if Vs is equal to Is times R. And if they're open-circuited, they're also equivalent if Vs is equal to Is times R. Okay, turn this off. The voltage is equal because they're in parallel. Yes, the voltage is exactly. The voltage, terminals A and B is in parallel to R. And R has a current of Is flowing through it. And so the voltage from here to here is Is times R. And so if Is times R happens to be equal to Vs, these two pictures are basically the same thing, right? Because as the user of a circuit, you are only concerned with what's happening. These are the access points. This is like the wall outlet, right? If you plug a device into the wall, the only thing that you sense is the voltage and current that are coming out of that wall. And there are many different ways, there are many different circuits that can produce that voltage and that current to come through the wall when you plug something in. And that's the whole idea here, is that you can get different circuits that supply you with the exact same voltage current characteristics. this and move along. All right, we did this. If you only, yeah, you need, I mean, the reason that sticking a fork is bad because generally kids stick, you know, both two prongs of the fork, and so they complete the circuit. But if you only stick in one, I mean, I wouldn't do it. Just, I especially since this is going online, don't ever stick forks into an outlet. But yeah, you do need to complete the circuit for the current to actually flow, right? So in this picture, if you touch A, but you do not complete the path to B, you're not going to get any current unless there's somehow a complete path. Okay. So source transformation you can do with dependent sources. So in this picture is equivalent to this picture if Vs is equal to Is times R. So keep in mind that if you replace a battery with a current source, the current arrow has to point in the direction of the positive pole of the battery. I mean, I think that's pretty intuitive, right? So you need to make them line up. And don't try to do this with if the resistor is equal to 0, right? So you can only do this technique if you actually have a finite, a non-zero resistance. And don't do it if it's infinite either. So don't do source transformation for circuits where this R is equal to 0 or infinity. Alrighty, we have our first source transformation problem. I like these questions. I think they're intuitive, they're useful. You will sometimes do this in the homework, maybe even on an exam, maybe just at home for kicks. So we are asked to use source transformation to find V naught. Right, so this is V naught here. We have two sources in this circuit. We have a battery that's in series with a 3 ohm. We have a 3 amp current source pointing down that's in parallel with a 4 ohm. So I think for the first one, I'll do it. I'll just demonstrate this for you guys. I'll show you how to transform this circuit in such a way that solving for V naught is easier. Okay, so the first thing that we're going to do, as probably many of you have guessed, is we're going to take this section of this section of the circuit that I'm highlighting, and replace it with a battery in series with a resistor, right? So 3 amps times 4 ohms is 12 volts. The reason the plus is on the bottom is because this current source is pointing down. And everything else in the circuit is fixed. So we've essentially, everything to the right of this imaginary line that I'm drawing is everything to the right of this imaginary line. Right? Nothing has changed. This section is the same as this section. But now we've replaced the 3 amp source in parallel with a 4 ohm battery with a 12 volt source in series with a 4 ohm resistor. Sorry. So is there any questions as to how we went from here to here?
Can you repeat that, Professor? I'm really confused.
Sorry, yeah, absolutely. So, imagine, look at this, everything to the right of here is going to stay the same, right? So this is what's changed is that this 3 amp, this is a current source in parallel with a resistor, which has been replaced with a battery in series with that same resistor. So like, just like in the previous, can I get back? right? So we said that these two pictures are equivalent, right? So we can swap out a current source in parallel with a resistor, with a battery in series with that resistor. So that's what we're actually doing here, right? Basically, we're just replacing this component of the circuit with a battery in series with this 4 ohm resistor. And the reason that we can do that is if you were to look at this circuit between this terminal and this terminal, it would be the same as if you were to look at this circuit between this terminal and this terminal. So, I mean, if that still doesn't make sense, I think let's go through a few more examples. And did you also rotate the structure? Oh, no, I did not rotate anything because remember the battery, the positive end of the battery has to point in the direction of the current direction arrow. So no, let me show you another way. Maybe I know what's causing the confusion. Let me do something. Let's see. Escape. Let me actually, just for a second, I'll stop the share so I can. I think I know part of the problem is, for your understanding, is there was a swap of the order that happened implicitly. So if I have, actually I'm gonna draw. See.
The 4A came from 12V over 3 ohms, right? On the right.
Yeah, the 12 volt came from the 3 amps times the 4 ohms.
Oh, it's on the left.
Yeah,
Okay.
but I'll show you why. So if you have this picture here, so it's gonna be ugly, but this picture is completely equivalent to this picture. Right, you can swap the order, right? So if you can move this 3 amp over here, right? You can move it over here. And then maybe it's easier for you to see how this became this. Basically, when everything's in parallel, you can move it which way. Does the direction of the current will always change. On the 4 amp, there's no 4 amp. There's a 4 ohm. And oh,
There's a 4 amp on the right of the second structure.
yeah, hold on. Oh, there's two things. Yeah, we haven't even yeah, I see. So this is the opposite. This is also a transformation where we've swapped a 12 volt battery and a 3 ohm resistor with a 4 amp current source and a 3 ohm resistor. So there's actually, sorry, I just realized there's two transformations from this step to this step. And one of the transformations is here, and the other transformation is here. So these are the opposite. Here you're taking a current source and transforming it to a battery. Here, taking a battery and transforming to the current source. Okay, you see it now. So yes, you still, the resistor always stays the same. It's only the value of Yeah, I like when people write O with many O's. It denotes a level of understanding. So the size of the voltage on the battery and the strength, the current source changes. The resistances do not change. It's just that when they're connected to a battery, they're in series. When they're connected to a current source, they're in parallel. Okay, so you have opposite transformations here. You have here a battery to a current source, here a current source to a battery. And the 8 ohm resistor is now here. Okay, good. People are seeing it now. That makes me happy. And then there's more transformations here. Now notice that we have a 4 ohm in parallel with a 2 ohm. So that's 12 volts in series with 6 ohms. So that can be replaced by a 2 amp in parallel with a 6 ohm. And so why do we do that? Well, we do that because now we can combine the 6 ohm with the 3 ohm into a 2 ohm. So when everything's in parallel like this, you can move them left and right, whichever you want. You're not changing anything because there are only 2 nodes in this circuit. There's the top and the bottom. And the order of the elements is completely arbitrary. Like you can, and you should verify this when you guys get your circuit kits, that you can move things around. And it doesn't change anything to the circuit behavior. And so now, so the 6 ohm here and the 3 ohm here have been collapsed into a 2 ohm because 6 and 3 in parallel make a 2. And there's one other simplification. We have a 2 amp source pointing down and a 4 amp source pointing up. Yeah, Sergio, I'm answering your question right now. So if you have a 2 amp source going down and a 4 amp source going up, it's equivalent to a 2 amp source going up, right? So again, if I move this over here, then you would see that they're partially canceling each other out. So whenever you see current source, just like if you have batteries in series, they sum up. Current sources in parallel also sum up. So hopefully you can kind of wrap your head around why that is. I guess another way of thinking about this is that this current source is trying to suck 2 amps from the top node. And this current source is trying to inject 4 amps into the top node. And so they're kind of, they're antagonistic. Okay, so yeah, Nashwin, that your question is, I know this causes people confusion. What has happened here? Basically the 8 ohm resistor has been left, and the reason that we leave it is because we are asked to find the voltage across it. So don't simplify something. Don't take something out of the circuit that you need to solve for. It needs to stay. But the 6 ohm and the 3 ohm are in parallel. And so 2 resistors in parallel can be replaced with a single resistor by taking the product and dividing by the sum. So 6 times 3 is 18 divided by 6 plus 3 is equal to 9. So hopefully that makes sense. So basically, remember that I can move this 6 to go right beside the 3, and then it'll be easier for you to see that you can replace, you can simplify the 3 ohm and the 6 ohm with the 2 ohm. Yeah, there you go. And so finally, now in this picture, we can use current division. So the 2 amps will be split across the 2 ohm and the 8 ohm resistor. So the current across the 8 ohm resistor through the 8 ohm resistor will be equal to 2 times 2 divided by 2 plus 8. So 2 times 2 over 10 equals 0.4 amps. And then the 0.4 amps multiplied by the 8 ohms gives you the 3.2 volts. So I'm a little bit concerned that I've lost many people here. So I'm gonna wait patiently, and if
I actually have a question.
yeah,
Isn't technically the 8 ohm resistor in parallel with the other resistors as well?
yes.
So why didn't
There's a
you
voltage across it. So you were trying to find a voltage, so you can't add into it.
that? All right,
Yeah. No. The only reason that we didn't include the 8 ohms is because the question is asking us to solve for the voltage across it, right? If we collapse this 8 ohm into the 2 ohm, we've lost the ability to know what's happening at it.
Okay, because I assumed that you could do the calculations and then like it could turn out to be like just pretend that the answer is like 3. It would be 3 times the times V naught. I thought it could turn into something like that.
So let's try to do it. I mean, I think what you're saying is actually right. Hold on. If you reduce the 8 and the 2, so that's 16, 1 point. Yeah, it would totally work, right? It would still actually work. You could actually reduce it and still get the voltage, right? If you reduce the 8 and the 2, 8 times 2 divided by 8 plus 2 is 1.6, and then 1.6 times 2 gives you the 3.2 volts. So it would actually work.
Okay.
So let's go through these. How did you get the 4 amps in part A again? Because 12 volts divided by 3 ohms is equal to 4 amps. Yeah, but in general, it's good practice to not touch any variables that we're looking to solve for. In step A, we did 2 yes. Yeah.
Professor, I have a question.
Yeah.
Do we actually do this in real life, or because I'm trying to find like uh relation between real life circuits and what we're doing on paper right now?
So what you're doing right now is like, you should think of it as like the foundation, like real life circuits. I mean, there are some cases where you will be building just a simple circuit, like a simple voltage divider. Like you're getting the voltage from a wall and it's too large for your device. And so you need to reduce that voltage. And so what do? You do a simple voltage divider. Like there are actually practical cases where you'll want to build a simple circuit. Yes, the final step is current division. So I'd say that you know, this is like foundational stuff for analyzing larger circuits. So the circuits in real life are huge. You know, oftentimes, I mean, first of all, the majority of circuits nowadays are digital, but you cannot understand digital circuits until you understand analog circuits. Also, in biomedical applications, you do a lot of analog amplification. You do a lot of measuring very weak signals, and so you're working with like bioinstrumentation systems that are analog, at least at the front end, and then they get digitized. So, you know, and again, part of it also is just like logic. Like there's learning the specific content that is presented in each of your courses. But then there's the overarching process of learning how to think logically. And I think that that's something that it takes a while for you to understand that, first of all, that's happening throughout your curriculum. But in what you are more important than anything to do with circuits is the fact that you're learning how to think like an engineer. So you have a set of axioms, like first principles, like this is like the foundation. And then you use those axioms to, you know, in rules, you have a set of rules that are valid, and you use those rules on those axioms to build up and analyze systems. And so I think that whether or not you will use source transformation, I mean, the other thing is, like, sometimes you'll be in a situation where you may be missing a battery or a current source, and so you still need to build the same circuit, but without that component. So it's useful to be able to know how to swap out certain components for others. But again, I think the more important thing is that you know how to apply, you know how to think logically, you know how to apply, you know what the valid operations are, and you know how to solve a problem by applying only what is valid. Yeah, so I think that.
And also to add to that, like this kind of like information is really helpful when, like, for example, you have an MCU, a microprocessor controller unit, and like you look at the data sheet and like they say, okay, for this pin, the requirement input is, for example, 4 volt, but like the output from a sensor is something in a different like voltage level. So you need to have a kind of like an intermediate circuit to transform like this voltage value in like from the output from one source to the input into the other source for it to be processed, and then like you need to have another like smaller circuit, like in real life application, even though you don't have to design this thing, but like it's really helpful if you understand like this kind of analysis that happen of these smaller circuits that come in and out of each of the pin, and like you can understand what like the designer is trying to do. Like I don't think we actually design it. I cannot design it, but like understand this thing really help you to understand like what is like the underlying principle of like for example an IMU or a MCU is doing.
Yeah, exactly. There are many times where you want to use a device, and that device has specifications, and you need to conform your peripherals to that device's specs. You need to be able to understand current voltage characteristics, power characteristics. So it's absolutely foundational. Thank you, Sam.
Thank you, Professor. Thank you, Sam.
All right, so another example, I'll switch the slideshow here so I can animate this. Find I naught using source transformation. So we are asked to find this current here in the circuit. So can anyone suggest some transformations that could be done here? Which parts of the circuit could you transform?
Can we combine the 1 ohm and the 4 ohm, and then that's in parallel with the 3 amps?
Yeah, so that would transform to a voltage of how much?
$15.
Yep, 15 volts. I hope that's what happens. Yeah, that is what happens. And we also do the same thing on the left. We have a 5 amp battery and a 6 ohm resistor. And we can swap it out with a 30 volt battery in series with a 6 ohm resistor. And so now notice that our circuit only has batteries. And that's a good situation to be in. It's easier to analyze circuits that don't have mixed sources. And so now the question is, what technique can I use to solve for the current flowing through the 7 ohm resistor?
Mesh analysis.
Mesh analysis, thank you. Mesh analysis is exactly right, right? You can write your KVL equation. So notice these are easy to write. So there's 9 ohms of resistance in the first mesh, and there's 3 ohms in common between meshes 1 and 2, and there's 0 ohms common between meshes 1 and 3. Now let's look at the second mesh. There's 3
I'm
plus
sorry, really quick.
7.
How did you get the 15?
Yeah, so we had a 3 amp source
Mhm.
in parallel with 5 ohms of resistance here.
Okay, because they're in series.
They're in series, exactly. So they simplify to a 5, and then you transform the 3 in parallel with a 5 to a 15 in series with a 5.
Okay, thank you.
No problem. So then you have 10 ohms of resistance in mesh 2, that goes on the diagonal. 3 of those are common to mesh 1, and 7 are common to mesh 3. And you do the same thing for mesh 3. 12 ohms, that's total in mesh 3, and then 7 of those ohms are common to mesh 2, and meshes 1 and 3 have no resistance in common. And the terms on the right side of this equation just correspond to the values of the batteries, where a voltage rise is given as a positive and a voltage drop is given as a negative. Doesn't matter where we place the 5 ohm resistor after adding. Yeah, so it's a good question. The answer is no, because you could swap. Remember, I said you could put this 3 amp to, you can swap the position of the 3 amp and the 5 ohm resistor here, and it wouldn't change anything, right? And so I believe that whether you put, let me just double check that. I believe that you could put, and that, yeah, I believe that you could swap these two. The 15 and the 5 ohm resistor and the 15 volt battery, I believe, could be swapped, and it wouldn't change anything to the circuit. It wouldn't change anything to these equations, actually, right? Because the 15 volt battery would still only be in mesh 3, and the 5 ohm resistor would still only be in mesh 3. And so you would get the exact same system of equations here. And I forgot to I have not been reading the questions. I'm not learning from my YouTube novice mistake. So I will read this one. Professor, you're doing a great job. Oh, you didn't say that actually. Doesn't matter where we place the 5 ohm resistor after adding 1 ohm and 4 ohms. So you're asking whether the 15 volt and the 5 ohm resistor could be swapped. Yes, they could be swapped, but it wouldn't change the dynamics of the circuit at all. Okay. All right, and then we can solve the system of equations, and I naught is equal to the difference between I2 and I3 is equal to 1.78 amps. And that's our answer. All right. Another question here. I think I like this one. We are asked to find Vx. In this circuit. Notice we have one battery another battery, and here we have a current source. So what do you suggest should be our first step in tackling this circuit?
Do we transform the 0.25 current source with the 4 amps and make it
Right.
into voltages?
Yeah, so you would what would be the what would be the power of the battery that we would replace it with? That's right. 1 VX. Exactly. And that would be in series with oh, and there's one other thing. Yeah, it's okay. You didn't have to do this. I did it here for a reason, but anyhow, so let's just for now focus on the first change, which is what I asked you about, which is what you do to this current source. And so I've transformed the 0.25 VX current source in parallel with a 4 ohm to a battery whose value is equal to 4 times a quarter VX, which is just equal to VX, in series with the 4. Couldn't we also do SC on the 2 ohm resistor? What is SC? Short circuit? I don't know. What does SC stand for? SC, source transformation. Yeah, we actually do it, right? We have a 6 volt in series with a 2 ohm, and that gets transformed into a 3 amp in parallel with a 2 ohm here. So this section of the circuit has been transformed to this section. And that will help us because now what can we do over here? Yes, this also has 2 source transformations. But just to let you guys know, there's like a million different ways of solving these circuits. So there's not going to be a single set of steps that magically yields the answer. There's multiple ways of getting at the answer here. So don't worry if you didn't see this particular recipe in you know, when you looked at it. What's the next step that you guys would do here?
You could combine the two ohm resistors to 1
Yeah,
ohm.
exactly, to a 1 ohm. And I believe, if memory serves me right, that would then allow you, well, you could also do another transformation here. I wonder if we will. Yeah, exactly. So now you have a 3, so now we've replaced the 2 ohm resistors with a 1 ohm, and that's still in parallel with this 3 amp current source. So now what you can do is combine the 3 amp in parallel with a 1 ohm to a 3 volt in series with a 1 ohm, right? And so now and the nice thing about this is now we have a single loop. And we are asked to find Vx. So where is Vx now in this circuit? And this is the tricky part. Notice that Vx is defined as the voltage from here to here, which is really this source transformation produced this branch. And so the Vx is defined as this voltage, which is now this voltage. It's a little bit tricky to see, but the Vx remains the voltage between the positive end of the current source, which is now a voltage source, and the ground node. The ground node is always at the bottom. Okay, so the question is how, I mean, one easy way now of solving for Vx would be just to apply KVL to this loop. We have a single loop, but we could just add up the voltages. So we have -3, plus I1 plus 4I plus Vx plus 18 is equal to 0. Yeah. I'm not surprised, right? Okay. So the questions are, I don't understand how you place Vx. And two other people are also saying that they don't follow the Vx placement. I agree, it's not immediately obvious. So Vx in this picture is across the 2 ohms. Hopefully you guys see that, right? And so it's between this point and this point. And in this picture, it's across the 1 ohm resistor. Right? All we've done is everything's in parallel here. So Vx is in parallel to the 2 and the 2. So it's still just in parallel with the 1. You're still looking at the voltage between the back end of the 4 ohm and the ground node at the bottom. Yeah, it's across the 1 ohm. Vx is equivalent to the voltage across the 1 ohm resistor. The tricky part though is now the 1 ohm resistor gets transformed and now it's in series with the battery. And so your Vx is still remember, it's like, imagine cutting the circuit here and replacing everything to the left of that with a battery in series with a resistor. What other way can we solve this problem? Well, you could do, let's see, you can do nodal analysis, right? You have this node is sitting at 6 volts. This would be your unknown node. This node is sitting at 18 volts. So Vx is placed like this because Vx represents the voltage from this point to the ground, which is still here, right?
But Professor, isn't it in association with the resistor? So like, that's how I was doing it. Like I was associating wherever the resistor went, the Vx also followed.
Yeah, the problem with that is that this resistor is in this picture where my cursor is now, that resistor is connecting the 2 points in the circuit that you are interested in. That's your Vx. But that is no longer the case for this 1 ohm. This 1 ohm resistor is not the same as this 1 ohm resistor because they are connected to different nodes in the circuit.
We keep the placement the same throughout them.
Yeah, the Vx has to correspond between the voltage difference between this point and the ground, right?
Got it, thank you.
Yeah, you're welcome. All right, so now let's do our KVL equation. So -3 plus 5i, that's 1i plus 4i plus Vx plus 18 is equal to 0. And we also can apply KVL to this imaginary subloop here. Right, so we have -3 plus I plus Vx is equal to 0. And now we combine these two equations. So 2 equations, 2 unknowns, and we get a Vx of 7.5 volts. I can't say I'm thrilled with the way that this example unfolded. The goal of this example is to teach you source transformation. And so as a result, the steps that were shown here are maybe, you would not have taken those steps if the question said find Vx in any way possible. But these are the steps that you would use if you really want to get comfortable with source transformation. All right, let's do, let me see how we're doing for time, 23. Am I on the next slide here? Okay, I'm gonna skip this practice. No, let me not skip it. It's one slide, and I think this one is easier. Okay. So we are asked to find Ix in this circuit. So we have a couple places here that we could perform a source transformation. We have the 4 amp source in parallel with a 10 ohm, and we have a 2Ix battery in series with a 5 ohm. So let's perform a source transformation only on the right side here. So we have a 5 ohm in series with 2Ix. So the equivalent current source is equal to 2Ix over 5. Notice this is a voltage. Even though it's written as a function of a current, it is a voltage. And so use Ohm's law to transform the voltage to a current. And so now you have a circuit that's pretty relatively easy to solve. I mean, there are many different ways you can solve it, but one way is just to apply KCL basically, right? This current is 4. The current here is V over 10. The current here is V over 5. And the current here is 2Ix over 5. So if you look at, let me see if I can annotate this, because I think this one is easier to see than the other ones. If you look at this node here, right? If you have this node here, you have one current flowing in, and that's 4 amps. And you have 3 currents flowing out. And those 3 currents are V over 10 plus V over 5 plus 2Ix over 5, or 2/5 Ix. I'm going to stop here just to make sure that everyone's followed me to this point. Okay. I'll take the silence as good news, even though it rarely is. So now, what else do we know? Well, I know that I've lost my cursor for the 10th time in this lecture. Okay. Remove. So the other bit of information that we have is that this Ix here, that's defined as the current flowing through the 10 ohm resistor, multiplied by the 10 ohm has to equal to V, right? Because V is defined over here, right? All of this node is sitting at V volts. And that's the voltage over here. And so we know that V has to equal to 10 Ix. So now all we have to do is substitute 10 Ix for V here, and we solve for Ix, which is 1.18 of an ampere. And we're done. So this was a much simpler case where we could have solved this problem with mesh analysis, for example. We could have drawn one mesh here and a second mesh here and solved it. But an alternative way did not require any mesh analysis. It just required basically KCL. Was obtained by transforming this part of the circuit into a current source in parallel with a resistor. And now you were able to write a KCL equation in this node and combine with Ohm's law across the 10 ohm resistor. We know that Ix has to equal to 1.18 amps. All right, so now we have arrived at the midpoint of this lecture, and we're going to cover a theorem called Thevenin's theorem. The final term in the KCL says 2 over 5 Ix. Yeah, that's right. Yeah, I should have written this 2Ix over 5. It's just equivalent to this term. Right, so the question was, about this term here, it is exactly equivalent to 2ix over 5. Okay, so Thevenin's theorem. This is important, especially for you guys in the class, because there's going to be a Thevenin theorem question on the midterm. And so what is it? It's just, it's a way of taking a complex circuit and replacing it with a simple one. And so one of the premises is that part of the circuit is like, again, I like to use this analogy of what's behind the wall is the circuit and the outlet is like your interface. Your outlet is what you care about. That's where you plug in your devices. That's where you plug in your load. Okay, it's called, so whatever you plug into a circuit is called the load. And the other element, so what's behind the wall, is fixed. And so you do not want to have to analyze everything that's behind the wall. Maybe what's behind the wall is constantly changing. So Thevenin's theorem provides a way to basically take a complex circuit and reduce it into a single battery in series with a resistor. And so we're going to replace everything that's behind the wall with a battery in parallel with a resistor. And to the user, you know, from the standpoint of someone who's just plugging something into that outlet, it's all the same. Right? So you're, in a sense, you're abstracting away the complexities of the internal circuit. So let's look at a kind of a diagram of this. Just move this chat window out of my way here. Okay, so in this picture, we have some linear circuit that has two terminals, and that's where you plug in your load. Thevenin's theorem says that as long as this circuit is linear, then it can be replaced with a battery, which we call VTH, TH for Thevenin, in series with an RTH. Right? So as long as, no matter how complex the circuit is, it can be replaced by a battery and a resistor. And as long as the voltage and current characteristics in these two pictures are the same, then these two scenarios are equivalent, right? So as long as the current coming out of the circuit and the voltage across your outlet, across your inputs, is consistent across these two, then it is valid to pretend as if what's in the circuit is just a battery and a resistor. So the load may be just a single resistor. It can also be a whole other circuit. And everything that's encapsulated, so this VTH RTH is called the Thevenin equivalent circuit, right? And so you're substituting a battery and a resistor for this circuit. All right. So now, like, kind of some justification for why we are able to do this. So if the voltage and the current relationship at your interface, at your terminals, is equivalent, then for all intents and purposes, the two circuits are equal, right? So let's look at what will make these two pictures the same. So again, let's take the extreme cases. Let's take the case where it's open, where we open circuit A and B. Well, if you open circuit A and B here, all you're sensing is VTH, right? Because this resistor effectively becomes dead, because by virtue of open circuiting this this part of the circuit, in other words, by removing the load, all you're sensing is the VTH. On the other hand here, what you're going to sense is whatever this circuit produces in an open circuit configuration. So for example, the open circuit voltage of the wall is what? What's the open circuit voltage of the wall outlets in your house? If you have nothing plugged in, what's your outlet sitting at? And just for those of you in North America, 0? No, that again, that's a common, it's not 0. There is a voltage, right? If there was no voltage, then none of your devices would work, right? Because that voltage is what yes, thank you. It's 120 volts in North America. I believe it's 220 in Europe, and I don't know what it is in Asia. It may actually, I'm not sure about the 220 in Europe. I think it's 220, but it may be 240, or I don't know. So in North America, it's 120 volts. Right, so that's your open circuit. Yeah, thank you, Christian. And so that's whatever if you just don't plug anything in, whatever, excuse me, if you don't plug in a load, whatever you observe at your terminals, that's your Thevenin equivalent. So again, oh yeah, we're getting a history lesson here. Very nice. Thevenin's theorem states that a linear two-terminal circuit can be replaced by an equivalent circuit consisting of a voltage source, VTH, in series with a resistor, RTH. And so the trick to doing all this is you're going to be given a circuit and you're going to be asked to replace it with a battery in series with a resistor. That's easy, but you need to know what the values of VTH and RTH are. And that's what the rest of this lecture is about, is how do you determine VTH and RTH? Fortunately, it's not too bad. So now, how do you, there should be a question here. I feel like we skipped over. How do you determine RTH? Well, with the load disconnected and the terminals open circuited, we turn off all independent sources. So we go into the circuit and we disconnect all the independent sources. Then the input resistance of the dead terminals over here must be equal to RTH because the two circuits are equivalent. So in other words, to determine the value of RTH, we have to look into the circuit with all of the sources turned off, right? So if we turn off all the sources, all we're going to sense is some input impedance, and that input impedance then becomes our RTH, because if we turn off VTH and we look into this circuit from terminals A and B, all we see is that impedance RTH. Okay, so what we're going to do to figure out the value of RTH, we're going to turn off all the independent sources in the circuit. We do not turn off dependent sources. We leave those in, but we turn off the independent ones. And that's what brings us to these two cases. Case one is the easy one. If your network doesn't have any dependent sources, you turn off everything and you just count up the impedance looking into terminals A and B. In case two, when your circuit does have dependent sources, we again turn off all independent sources. However, there's going to be an extra step required to find the input impedance. And what we're going to do is we're going to apply a test voltage. So we have, so V naught here is going to be a test voltage. So here's our circuit. It has some independent sources that have all been turned off, but it also has dependent sources. And so what we're going to do is probe this circuit by applying like a 1-volt battery and seeing how much current ends up flowing into the circuit. So this is a common technique used in circuits. You apply a known voltage and then you measure the current, and the ratio of the test voltage to that current is your Thevenin resistance, right? So again, if you take a 1-volt battery and then you have an ammeter which measures current, and that ammeter measures how much current ends up being sucked into the circuit, the ratio of that test voltage to that measured current is your Thevenin impedance. Another way of doing it is to apply a test current, right? You can also apply a 1 amp current and measure what the voltage is that emerges across terminals A and B. And again, you then use Ohm's law to figure out the value of RTH. So in other words, you put in a 1 amp source and you take your voltmeter and you see what the voltage that's produced across terminals A and B is. And that the ratio of that voltage to the 1 amp gives you RTH. And you'll get the same result whether you apply a test voltage or a test current. And you can use any value for the test voltage. It doesn't have to be 1. Okay. So basically, Thevenin's theorem is useful because it says that large circuits may be replaced by a much simpler circuit consisting of a voltage source in series with a resistor. Right, so if we have the box represents our complicated circuit, right? And we are interested in knowing what happens if we apply our device, our load, RL, to that circuit. Well, the way you do it with Thevenin analysis, you substitute this box with a battery in series with a resistor, VTH, RTH. And then you apply your load to that simple circuit. And then you can just use voltage division or Ohm's law to figure out the value of IL. Can I explain impedance? Impedance is just another word for resistance. I'm not sure that's what you're asking for. When we get to AC circuits, you'll see that impedance impedance can have a phase, a magnitude and a phase, but resistance is just, when you're talking about DC circuits, they're equivalent. I think we've gone over, I use them interchangeably. They're basically the same thing, except that impedance, strictly speaking, impedance can be a complex number. When we talk about AC circuits, we're going to talk about phasors, talking about sinusoidal circuits. But for the sake of this part of the course, DC circuits, there's no difference. They are equivalent. Impedance equals resistance for DC circuits. You saw the equation for impedance. It's complicated. Where did you see the equation? Someone's had enough. Oh, don't worry about it. We'll cover impedance later in this course, like the complex impedance. It's the exact same thing. It's just voltage divided by current. For DC circuits, the voltage is a real number and the current is a real number. And so it's just a ratio of voltage to current. For AC circuits, it's a complex number divided by another complex number. So it isn't, it's just a matter of knowing how to handle something called the phase, which we'll get to. Okay, so you can replace your circuit with imaginary, yeah. So there's gonna an impedance when you're talking about AC circuits will have a real part and an imaginary part. But for DC circuits, the imaginary part is always 0, so you can just ignore it. So now we've replaced our circuit with a battery in series with a resistor, and we're interested in how much current our load draws. And so we can use voltage division, right? Or yeah, we can, so this IL is equal to VTH divided by the sum of RTH and RL. And so the voltage drop across the load is equal to the source voltage, which is a Thevenin voltage, multiplied by the load resistance divided by the sum of the total resistance in the circuit. All of this will become clearer once we do a few examples. Okay. This is our first example of a Thevenin analysis. We are asked to find the Thevenin equivalent circuit of everything to the left of terminals A and B. So everything here, we are asked to find the Thevenin equivalent circuit. So let's go. I'm going to take you through the steps for this one to demonstrate how the analysis works. So there's 2 steps. They're the line through RL. So that means variable resistor. So here we're being told that our load can be 6 ohms, 16 ohms, or 36 ohms. So you can buy resistors that have variable values. And so you dial the little knob and then, yeah. Pretty cool stuff, I know. 2 steps to Thevenin analysis. Step 1 is to disconnect the independent sources and figure out the input impedance looking into the circuit. So we disconnect the 32 volt source, replace it with a short circuit, and we disconnect the 2 amp source and replace it with an open circuit. So notice that there's no more current source here. Right? And we are asked to find the input resistance. So if you're looking into the circuit from the right to the left, how much impedance do you see over here? Who can, I want some help for this. Who can tell me the value of RTH? What I really need is sound effects. So when someone gives the correct answer, I can I press a key and it makes, whatever sound effect is best associated with the victory. And when someone gets it wrong, I can play that buzzer. I think Zoom should definitely add that feature. 3/4. 4 is correct. Thank you, Omar. Christian, good try. You're almost there. 3 is the combined resistance between the 4 and the 12, right? 12 times 4 divided by 12 plus 4 is 3 ohms. So the resistance from here to here is 3. So 1 plus 3 equals 4. Right? I'm going to work on those sound effects. It's going to really enhance the experience. Oh, I don't want to skip ahead. Now, the second step in Thevenin analysis is to open circuit terminals A and B and figure out the voltage, the open circuit voltage across A and B, right? So we open circuit A and B, so we remove the load. We leave our circuit intact. We put the independent sources back in, and we need to find what the voltage is across these two terminals. So what technique should I be using to solve for VTH in this picture? Mesh analysis, that is correct. So let's write our mesh equations. So we have minus 32 plus 4I1 plus 12I1 minus 12I2, right? So that gives us 16I1 minus 12I2 is equal to 32. That's mesh equation number 1. Who can help me? Who can tell me the equation for mesh number 2?
Would it be 12I1 minus 12I2 equals 2?
Um, 12. I'm trying to see what you're doing. So which meshes does the 2 amp source belong to? Yes, Christian, that is correct. Very good. I2 is just equal to -2, right? Because this current source only belongs to the second mesh. There is no third mesh here. And so I2 is just equal to -2. So now we can solve for I1. I1 is 0.5 amp. But this last step is the part that I think confuses people. VTH is equal to this. Why is this VTH? This is the part that, so VTH here is 12 times I1 minus I2. So I1 is 0.5 amp. I2 is -2. So it's 12 times 2.5 equals 30 volts. But I want to know, why is it that I can take VTH, which is originally defined over here, and place it over here? Why was I able to do that?
Is it because the 12 ohm is in parallel with the voltage?
It is, but
Okay.
why is it in parallel with the
Oh,
voltage?
why?
I mean, your answer is correct. It is absolutely in parallel. But what about this 1 ohm resistor?
Is it dead?
Yes, exactly. It's dead because we've open circuited terminals A and B. So you can, for all intents and purposes, you can ignore this resistor. You can just treat it as just a piece of wire. And therefore you have a wire that's connecting this node all the way over here. Oops. And that is why VTH can be expressed all the way over here. And so now we have everything we need. We have the RTH 4 ohms and we have the VTH 30 volts. Right. So this is our Thevenin circuit. 30-volt battery in series with a 4 ohm source. And now we can solve for IL for different values of RL, right? Remember that the value of IL here is given by Ohm's law as 30 volts divided by 4 plus RL, right? Because 4 plus RL is the total resistance and 30 volts is the total voltage. And so we can compute that for various values of RL. I think you all know how to do this. So for 6, it's 3 amps. For 16, it's 1.5. And for 36, it's 3/4 of an amp. Okay. Let us move on to more examples. Find the equivalent circuit to the left of terminals A and B. So again, we have, oh, sure. Question is, I still don't understand how you got RTH. So remember, the procedure with RTH is to disconnect all, you're just interested in the impedance. So you disconnect all the sources, right? So you short circuited this battery and you've open circuited the current source. And all you're left with is this. Do you understand this picture? How we got it? Good. So now the 4 ohm and the 12 ohm are in parallel because the top end and the bottom end are the same. Right? So we can replace the 4 ohm resistor and the 12 ohm resistor with a single 3 ohm resistor. 4 times 12 divided by 4 plus 12. That's 3. Plus, they're in, and these two resistors together collectively are in series with the 1 ohm. Okay, yeah. You'll get it. We'll do a bunch more. You're very welcome. All right. So in this problem, so again, let's start with RTH. Remember, to find RTH, we disconnect all our sources. So this is going to be a short, and this is going to be an open. So this is really going to simplify our circuit, right? Because this branch is gone, and all we have is a bunch of resistors. But now we are looking, I really should have, I'm going to annotate this to make this more clear. Right, we are looking into the circuit from the terminals A and B. Okay. So what if I'm looking right to left, I'm looking into the circuit, how much impedance do I see over here?
16 ohms.
16 is a good guess, but it's not the correct answer. So one way of thinking about this that I found helpful was if I want to go from, we interrupt this, it's my cursor. Yes, 48 over 16 is correct, but let me just restore my cursor. Okay. So the way you should think about this is if I want to go from point A to point B, how much resistance am I going to encounter? So I can either take the 4 ohm path that's direct, or I can take the long way. And long way is take 12 ohm path, 6 plus 6. Both ways take me from A to B. In other words, this 6 plus 6 is in parallel with the 4. So we have a 12 in parallel with the 4, which means that our RTH is equal to 3 ohms. That's how, if you're ever unclear, if you don't see what the Thevenin voltage, Thevenin resistance actually refers to, just remember to go from A to B, what are my possible paths? Okay, now to get VTH, we open circuit terminals A and B. So we draw this, and again, I'm not gonna annotate this, but you have terminals A and B are over here. Okay, and we are asked, basically, we need to know the voltage across this 4 ohm resistor because that's where terminals A and B are defined. So what's a technique that I can use to solve this circuit here?
Nodal analysis.
What's that?
Nodal analysis.
Yeah, nodal analysis is good. I'm going to do mesh analysis. You could have totally done it with nodal analysis, but I'm going to do mesh analysis and do a super mesh. So you go minus 12 plus 6i plus 6 plus 6i1 plus 6i2 plus 4 is equal to 0. And then at the current source, which was here, we have that I2 plus 2 is equal to I1. Okay, admittedly, this is not the most, this isn't the best drawing to demonstrate the super, because the current source is missing, but it is actually here. It's the 2 amps pointing up. So we have I2 flowing in, 2 flowing out, and I1 flowing out. So now you have your KVL equation and your KCL equation. You solve those and you get that I2 is equal to 1.5 amps. No, you leave dependent sources alone. We'll get to that. We'll get to some examples of that. But you don't touch dependent sources. So if I2 is equal to 1.5 amps, what is the value of VTH here? Yep, 6 is correct. Thank you. VTH is 6 volts. So now we have our circuit. I will, okay. Oh, oops. I'm sorry. Let me just see. Going to. Let's see how many of these. I gotta pace myself a little bit. Maybe what I'll do is I'm actually gonna skip number 3. I'm gonna do number 2 for you, with you. I'm gonna skip number 3, I think. Okay. So another Thevenin analysis problem. So the Thevenin procedure consists of finding 2 quantities. One is RTH and the other is VTH. So here we have the case where we have a dependent source, right? So we disconnect the 5 amp current source, but we have to leave this 2VX battery intact, right? So our circuit, oh, we're doing VTH first. So let's do VTH. So VTH, we just open circuit A and B. And so A and B is defined over here. So the 2 ohm resistor becomes dead. So we're just gonna neglect all of this. And we're gonna be concerned with finding the voltage across the 6 ohm resistor. And that's gonna equal to our VTH. So we have this circuit here, and we are concerned with finding the voltage drop across the 6 ohm resistor. Okay, so what are some techniques that we could use to solve for VTH in this picture?
Can we use a node analysis?
What's that?
Can we use a node analysis for the centering?
Yeah, I think nodal analysis would work. Yeah, I think I use mesh. I don't know. I kind of went crazy with the mesh analysis in this slide deck, I think, but we could have done yeah, so let's do mesh analysis. We have meshes 1, 2, and 3. So fortunately, mesh 1 is easy, right? I1 is just going to equal to 5. Now mesh 2, it's also pretty straightforward. We just have 4 plus 2 plus 6 ohms of resistance along mesh 2. And 4 of those are common to mesh 1, and 2 of those are common to mesh 3, right? And so we have 12i2 minus 4i1 minus 2i3 is equal to 0. And since we know that I1 is equal to 5, we can just go ahead and substitute 5 into I1 here. And so what we have is 12i2 minus 2i3 is equal to 20. So now we effectively have just a two-dimensional system of equations. Because our final mesh equation is also very straightforward. We have 2vx plus 2 times I3 minus I2 is equal to 0. Sorry, minus 2vx plus 2 times I3 minus I2 is equal to 0. And we know that Vx just give me a second here. Yeah, so this equation here can be simplified to this. So all we've done is we've moved 2vx to the other side and we've divided both sides of the equation by 2. So we have that Vx is equal to I3 minus I2. What else can we say about this voltage Vx? How can we relate Vx to our mesh currents? Sergio, you say that it's equal to 4i2 minus 4i1. It's very close. It's the it's 4i1 minus 4i2 because the arrowhead of the I1 is hitting the positive pole of the battery, but that's very close. So now we can substitute this equation into, let's see, we can substitute 4i1 minus I2 for Vx. Let's see. Let's see what I've done here. It's been a while. What did I do? So I'm working with this equation. Boy, this is not going to make for good good YouTube content right here. This would be a good time for like those things that appear on the screen, like links and ads. Let me just try to, so we have Vx. So I would, looking at this, I would just substitute Vx into here. And then, but that's not what I did. Oh, right. No, actually, I did something much simpler. Yeah. Thank you. Who was that? Thank you, Sergio. That's exactly right. I just substituted 5 for I1. And so this becomes 20 minus 4i2. And then I equate that to I3 minus I2. So then I get my second equation in I2 and I3. So then I can solve for I2 and I3. So I get that I2 is equal to 10 over 3, and I3 is equal to 10 amps. So now my question to you is, knowing these, what is the value of VTH, which is defined as the voltage across here, across terminals A, B, given that I2 is equal to 10 over 3?
$20.
20 is correct. Thank you. I just multiply the 6 ohms times 10 over 3. Right? I get 20 volts. So now we're halfway done with this circuit. All we're left with is determining RTH. Or
Professor,
yes.
I have a quick question.
Yeah.
How did you get Vx equals 4I1 minus I2?
Yeah. So let me actually, what I'll do is I feel like we missed a whole step in this. We missed the whole, let me see something. I am going to answer your question. I'm just going to figure out what happened to the determination of RTH. Yeah, okay. So we actually skipped the page. But it doesn't matter which order you do it in. Let's see. We did this. And we skipped this and we did this. And your question is this. Okay. So consider this. Let me see if I can, so I can annotate it more freely. Basically, you have, if you look at this 4 ohm resistor, you have I1 that's coming in here, and you have I2 that's coming in here. And so the net current flowing from the positive to the negative end of the 4 ohm resistor is I1 minus I2. And so Ohm's law says that that net current multiplied by the 4 ohms is equal to Vx. Right, so this is whenever you have a branch element that is common to 2 meshes, the total current through the physical current across this 4 ohm resistor is the algebraic sum of the mesh current. So this mesh current is going down the resistor. This mesh current is going up the resistor. Hopefully that makes sense.
Oh yeah, thank you.
You're welcome. For mesh 2, question is, for mesh 2, why is it 12I2? I'm getting 6I2. Okay, let's take a look at that. Oops. Mesh 2, right? So you're summing up, so it's 6I2 plus, so if I were to, so I'm gonna write the KVL for mesh. Okay, you got it. Okay, good. Now I want to go back to I want to go back because we skipped the solution for RTH for this problem, which I want to do. Okay. So now to solve for RTH, we have to disconnect the independent sources, leave the dependent sources in, and apply a test voltage. So that's what we're going to do. We disconnect all the independent sources and apply a unit voltage at terminals A and B. So let's do that. So here is what our circuit looks like. We've gotten rid of the 5 amp current source. We've kept the 2Vx battery in, And now we've applied a 1 volt battery across A and B. And what we're interested in determining is the value of I naught, which is defined as the current that's going to flow from the test voltage into the rest of the circuit. And so what are some ways that I could solve for I naught in this picture?
Mesh analysis.
Yeah, definitely mesh. Here you would do mesh, yeah. Right, so again, you have 3 meshes, and they're different from the, notice that they're different from the meshes that we were solving for just a second ago to find VTH, right? So at mesh 1, we have minus 2Vx plus 2 times I1 minus I2 is equal to 0. Right? And here, Vx is easier to determine, right? The value of Vx in this circuit is just because Vx only appears in one mesh, in one mesh. And so its value is equal to negative I2 times 4. And so we plug that in here, reduce the equation, and you get 2I1 plus 6I2 is equal to 0. Let's move on to mesh number 2. Why did the upper branch move left? It didn't. We got rid of this branch because we disconnect the sources. Yeah. Okay, so now mesh 2, we got 4I2 plus 2 times I1 minus I2 plus 6 times I2 minus I3 is equal to 0. And that gives us negative 2I1 plus 12I2 minus 6I3 is equal to 0. And finally, the KVL of mesh 3, we get 2I3, that's here, plus 1 volt, because remember, voltage drops are treated as positive, plus 6 times I3 minus I2 is equal to 0. And so now we have 3 equations and 3 unknowns. And I'm sparing you of the algebra. And I'm just telling you that the value of I3 is equal to negative 1/6 of an amp. We're doing 2 separate mesh analyses because we're solving for 2 different quantities. We have one mesh analysis to solve for the input impedance, and we have another mesh analysis to solve for the Thevenin voltage. So that they necessitate solving 2 different circuits. Okay, so if I3 is equal to negative 1/6 of an amp, we'll see. It's the first time you're seeing it, so you should not. You do another 500 of these. It will seem a lot easier. And so I naught is equal to negative I3, right? Because I naught is defined in the same mesh, but it has opposite polarity. So the value of I naught is equal to 1/6 of an amp. And so 1 volt divided by 1/6 equals to 6 ohms. In other words, for this circuit, the Thevenin impedance is equal to 6 ohms. And so that circuit can be replaced. Oops, I didn't mean to do that. All right, so we already solved for VTH. We just did it out of order. I apologize for that. So that original circuit can be replaced with a 20-volt battery in series with a 6 ohm resistor. So this is our original circuit. So we've replaced all of this with a battery in series with a resistor.
Professor, can you explain where the 1,6 came from?
Yeah, sure. You have to go back to this mesh problem. So when you solve this mesh analysis problem, you get that I3, this third mesh current, is equal to negative 1,6. And so I naught is just negative I3. And so it's equal to 1,6.
Okay, so I was just solving for the mesh analysis.
Yeah, all it is a solution of the mesh analysis.
Okay, thank you.
You're welcome. Okay, I'm gonna skip number 3 because I feel like it's not one of the okay. I'm gonna do this one instead. We are asked to find the Thevenin equivalent of this circuit. And these questions are interesting. So this is a circuit that does not have any independent sources, but does have a dependent source. So something funny happens here and you'll see it. So first of all, let's solve, who can tell me who can take a guess at the value of VTH for the circuit? So remember, VTH is the open circuit voltage across A and B. So I'll tell you, I'll give you a hint. It does not require doing any math whatsoever. No math, no circuit laws. You can look at the circuit and deduce that the value of VTH is equal to
Zero?
very good. It is 0. The 3 of you got it. Excellent. It is 0 because there's nothing providing power into the circuit, right? There's no source of power here. So VTH has to be 0. So anytime you see a circuit that has no independent sources, you know that the Thevenin voltage has to equal to 0. So that's the really easy part. Now for RTH. So for RTH, we need to apply, so we could have applied a test voltage, but since we have a current source in the circuit, let's apply a test current of I naught. And our RTH is going to be the ratio of the voltage across terminals A and B and that I naught. So we need to find, I don't know what total circuit voltage means. Thevenin voltage is the voltage that appears at the inputs into the circuit. So total circuit voltage, I guess you mean like the total voltage everywhere, but it's not a well-defined term because the sum of voltages, along a loop, for example, is equal to 0. So Thevenin voltage is the voltage that appears at the input into the circuit. All right. So Ix is defined over here, and the current here is defined as 2Ix. So how can I solve this circuit? Let's say I want to solve for V naught. I'm interested in this V naught because the ratio of V naught to I naught is going to give me RTH. So how do I solve for V naught in this circuit? Which technique would you use?
Are we using mesh analysis again?
Here I would use nodal analysis, and I hope I did. I can't remember. Yes, I did. Because we have only current sources. So whenever you have current sources, that's a good situation for nodal analysis because in nodal analysis, you're doing KCL. So let's look at this node here. But you could do it with mesh. It wouldn't kill you. You would still get the right answer. It's just as easier with nodal analysis. So at this node, oh, we have a question. Go ahead.
Yeah. Why do we use that node and not the one that's closer to the source?
Very good question. You're saying why don't we use this one?
No, right above the 2
one?
ohms.
Oh, this one?
Yeah.
It's all the same. Actually, we could have labeled it here, right?
Oh, okay.
This is V naught, this is V naught, this is V naught, this is V naught, this is V naught. This is everywhere you can trace, it's all V naught. We could have easily labeled it here. It wouldn't make sense to put it here because this is a current source. We don't know how to find the voltage across the current source easily. But we could have labeled it anywhere. We could have put it anywhere along the top here.
Okay, thank you.
You're welcome. So let's do nodal analysis. We have I naught. We have, what do we have flowing in? We have, I'm gonna draw my little circle here. We're applying nodal analysis here. So we have Ix plus I naught flowing in, right? These are these two terms here are these two currents that are flowing into the node. And what's flowing out is 2Ix plus V naught over 4, right? So we have this current flowing out. This current flowing out, this current flowing out. And we have Ix and I naught flowing in, right? So now we also know that Ix here is equal to negative V naught divided by 2, right? So Ix is defined as flowing from ground up to V naught. So Ix is equal to 0 minus V naught divided by 2. Right, so now we can substitute that into here, and we've got that I naught. And then if we rearrange this, if we substitute this expression, if we substitute this expression here for Ix here and also Ix here, we end up with this. That V naught is equal to negative 4 I naught. So given this equation, what is the value of RTH? If V naught is equal to negative 4 I naught, what is the Thevenin resistance here? Yes, negative 4 is very good. That's excellent. Because their ratio, I lost my cursor for the 200th time. Let me see, quickest way. There we go. Negative 4 is correct because RTH is the ratio of V naught to I naught, which is equal to negative 4 ohms. So it's kind of it's a less than intuitive idea that resistance can be negative. But this only happens when you have a circuit that has dependent sources, right? So this source responds to an input, and you can think of a dependent source as kind of like it's sensing what's happening in another part of the circuit and it's injecting current. So in a way, it's doing the opposite of resisting, right? Because it's actually capable of producing power, or it's able to amplify whatever Ix is here, it doubles it over here. So that's one way of kind of conceptualizing how the input impedance can be negative, right? Because it only happens when there's no independent sources and there is a dependent source. So it tells us that the circuit is supplying power, right? So when we stimulate the dependent source, it gives us energy. It supplies power. Let's see. Okay, I'm going to stop here because I feel like we've reached the limit of tolerability and attention span. So I'm going to try to end my show. We're going to do this next class. I'll just stop my share. Okay. We will, so next class, we're going to finish up Thevenin analysis. I think this is probably one of the last, if not the last. Yeah, this is the last problem with Thevenin's analysis. We're going to finish it up next class, and then we're going to move into Norton analysis, which is very similar. So if you understand Thevenin, understanding Norton is very straightforward. Reminder that the first homework is due on Wednesday. Get it in by midnight on Blackboard. Also a reminder to please send your shipping information to Tariq, the TA, so that we can ship the lab kits to you. And other than that, have yourself a great 48 hours, and I look forward to seeing all of you guys on Wednesday.